Hello, everyone, and welcome to episode 45 of the Hyperthesis podcast. We have a very wide range of topics that we're excited to get into. But first of all, hello, everyone. I'm Patrick.
I'm Feely.
And I'm Leo.
Well, as I said, we have a bunch of topics that we're going to be diving into today. And we'll start with, as usual, with our introductory topics. So does anyone have anything they would like to discuss?
Before you start, I need to apologize for my probably poor microphone quality. So I'm currently traveling and just using my laptop microphone, but we'll come to that soon. Anyway, intro topics.
I thought today we're gonna be speaking a little bit about the fire, the updates on the fire, because, well, all of us are in Canada and two of us are in Ontario, which is got really heavily affected by the, I think, fire from Quebec that has a lot of smoke. I walked out the other day and the sunlight was surprisingly orange at like 1 p.m. I was like, well, that is kind of strange. I thought it was some kind of apocalypse going on, but it's just some scattering of light. But it shows how much smoke was in the air. I think my city was like one of the worst air quality on the planet for maybe a few hours or something. That was pretty crazy.
Yeah, it's very impressive to see how much the smoke has gone, especially from the Quebec fires. And it's affecting a particularly large amount of people because it's gone onto the eastern seaboard of the United States. And so it's something like 100 million people within the United States have been issued air quality alerts where it's not really the safest to go outside. And if you are in those areas and something is happening, we record a bit in advance, but if there's a lot of smoke outside, don't go outside. If you have to go outside, wear a mask because it's all those smoke particulates are definitely not good for your lungs.
So on my weather app, I have an iPhone. The index it uses for air quality goes from 1 to 12 for some reason. Does anyone here know how that index works? Someone I went to high school with, I wasn't really good friends with them or anything, but I wasn't, their enemy or anything. They're actually an air quality scientist in Nova Scotia now, and I was thinking about asking to bring them on the show at some point. That would be, because I'm interested in why is that index from 1 to 12, and how do they decide that?
My uneducated guess, my funny guess was like, normally it has 1 to 10, but there's so much pollution that need to start adding 11 and 12.
Oh,
oh, well, it used to be 10. It's like, bad natural fire is really bad. And then we realized that we have like factory pollution. That's like, oh, that thing is really bad. So let's put 11. And then we realized that we have even worse case of pollution. Like, well, let's make them 12. But I'm sure there's more formal definition of air quality once like different thresholds they need to reach, like in terms of particle size, density, and stuff.
Yeah, I think the scale's from 1 to 12. I could be wrong, but so yeah, it's been pretty bad in Ontario. It's kind of mind-blowing how far the smoke from forest fires can go. And we talked about this in a previous episode that specifically focused on forest fires for Nova Scotia and British Columbia and Alberta, but this is my first time kind of experiencing it, especially in Ontario. So, like, the air quality index where I'm at right now is actually not too bad. It's on a 4 out of 12, so it's not ideal, but for the last few days, it's been hovering around like 6 to 7. And in Hamilton yesterday, where I live, it was actually a 10, which is like very smoggy and red and it kind of just smells like campfire everywhere.
And so just to go back just on air quality index quickly, the 1 to 12, that's kind of arbitrary. And it kind of depends where you are. So for example, Canada uses specific air quality indices, which usually range from 1 to 10 and above. So if it's 10 and above, you're in trouble. Whereas like a more global index uses anywhere from 0 to 2 to 400. And so there are different ratings, of course. So, for example, in Canada, if it's a 1 to 3 out of 10, then it's a low risk. If it's 4 to 6, it's moderate. If it's 7 to 10, it's high. And then if it's anything above 10, it's very high. But each country kind of has its own standard, and there's not really a universally agreed upon standard, which is unfortunate, but there is a research project for someone.
Well, I think here usually it's really good, like 1, right? And for the past couple of days, it reached 11, which to me is like, wow, you can feel it. Like I walked outside and my eyes start to water, which is interesting. But it has been raining for the past day or so, so it tuned down back to 1, which is great. And also, I think as the wind change, there are a lot of other factors that contribute to air quality.
So something quickly I want to mention about wildfires is just some data from this year. So I'm very fortunate to work with a group that does the national burn area coverage each year. So each year they look back to the year past and sometime years past to try and figure out how much area was burned throughout the whole year, throughout the whole wildfire season. So this is something very important. So we know how much carbon is going into the atmosphere, how much land use has changed. But there was a really good article published by CBC, which actually features my boss's boss's boss, the head of the Canadian Forestry Service building here in Edmonton. And in that article from CBC is a nice plot. And so what it shows is the essentially burned area for each year. And so for 2022, the total burned area was about 1.57 million hectares. So 100 by 100 meters is a hectare. So 2022 was 1.57 million hectares. 2021 was a lot more at 4.22 million hectares. So quite a large area burned. And mind you, these are by the end of the year. Rough estimates currently from this year for 2023, just at the beginning of June, show that we are around 4.18 million hectares. So from the last about 10 years of data, we have reached kind of the maximum of those 10 years within the first month of fire season. Because fire season roughly starts around May, sometimes March 1st, but we have reached that in like a month than what's typically reached in a whole year from May to November.
Yikes.
It's insane.
Yeah, that ain't good. That is the opposite of good, if I've ever heard it.
But moving on to less depressing topics, Liam, what have you been up to this week?
Well, so I have been at a conference at Perimeter Institute in Waterloo, Ontario, and this is one of the first conferences I've gone to that's actually in my kind of direct area of study. So it's a conference it's called like, hold on, let me bring up the title of it here. It's called Quantum Simulators, but the official name of the conference is Quantum Simulators of Fundamental Physics. So as a recap, I mean, I've talked about this a lot before, but I study analog gravity. So I theoretically create things that mimic gravitational black holes out of these ultra-cold gases, these Bose-Einstein condensates. And there's a bunch of other ways you can do this. You can use water, you can use optical fibers, you can use graphene in solid-state systems. But this is a bit more general of a conference. It's not just for gravity, it's for cosmology models, which I guess are kind of quantum gravity, but like you can model inflation, like an inflationary universe with these. One thing you can do is you can model quark gluon plasmas, which I know very little about, but I think that's kind of cool. You can actually mimic crystal structures. So one problem with like crystalline structures that it's very complicated. So for example, if you want to study superconductivity, these solid state structures, it's so many different atoms and things together, and there's all this thermal noise happening. So you can create a system that's mathematically equivalent using lasers and magnetic fields and ions. You can create an optical lattice using light. You put these ions in, you tune it so that it looks exactly like these crystals. and then you can study the kind of fundamental physics very easily without all this background stuff happening, so you can get a very good picture of what's going on. And there's a whole bunch of stuff like that. So this conference has kind of been related to that, both theoretical and experimental venues. And there's some pretty big names in my field that are here. I got to meet Bill Unruh himself, have some good conversations with him. So that's been pretty cool. He's like, we've talked about him a lot. There's a physicist, Silke Weinfurter. She's kind of the big name in analog gravity. You might have seen it, but she's created this kind of water table with a vortex in it, and you can get analog super radiance and all these other things out of it. So she was one of the first people to study this, and so she's been kind of running the conference actually at Perimeter Institute. And there's all these other names, but it's been great. I had to present, and it was kind of my first time that I got to present my work in front of people who actually knew what I was talking about. So I was very nervous, actually. I was sweating.
Yeah, Willem Unruh is interesting because I think I don't know if we talked about Unruh radiation and stuff, but I remember doing it for like a theory club or other thing. So I explained it mathematically. It's really neat. It's really niche. And what did they say about your work? Do you think is what did they say?
Well, he didn't say anything. He didn't ask a question.
What's the word on the street? What's how your street cred after your presentation?
People are pretty interested in it. You see people kind of interested in caustics and catastrophe theory, as it's always kind of floating in the back of their head, but they don't care about it too much, which is valid. I understand. But they're always very interested when you talk about it, and they're always, I don't know, they appear everywhere. There was someone who gave a talk on how you can sometimes you can treat a black hole like a scattering problem. So in particle physics, the scattering problem is that you fire in a particle, it interacts with some other particle, and it bounces out in some way, and you can model that using kind of approximations and things. But they were treating a black hole like a scattering particle and firing in light, but it was called a dirty black hole. So it was a black hole with all this stuff floating around it. Like, just imagine little asteroids or something, little pieces of rock. They're not close enough that they're part of like the immediate accretion disk, but they're pretty close to it. And they made a connection to rainbows and these optical phenomena called glories, these are things I love and am obsessed with. So I had a lot to say about her talk. It was a very good talk. I was really excited. So they showed that you can put this light in, and that actually you get a caustic coming out, the exact same thing you get for a rainbow from a black hole, one of these dirty black holes at least. So like, even when people are trying to study something else, you get focusing events everywhere. So they end up talking about caustics, whether or not they know it.
Well, it's a form of gravitational lensing, right? Like it's basically bending light, and if the condition is right, I don't see why it won't create.
Yeah, gravitational lensing though is a little bit different than a rainbow. Like a rainbow, the light comes in, it goes in the raindrop, and then it comes out the same way it came in. Whereas and it focuses in a specific way. It's a specific form of caustic, because catastrophe tells you that any focusing event can only take on certain shapes, and it turns out that shape is a little bit different for gravitational lensing than it is for this kind of black hole rainbow. Although it's not quite a rainbow, because I don't think the light gets split into its constituent wavelengths like it does when it goes through water. But the analogy was there, and there were some other caustic analogies. But yeah, so there's some interesting questions about my talk, but the two big names didn't really say anything. They were too busy organizing and running the conference, and also maybe they didn't care. I don't know. I know Silke Weinfurter, though. She published a paper a year ago specifically about caustics and catastrophe theory. I think it's her only paper on the topic, but that she knows about it. And she didn't look too confused, so I'm quite happy about that.
Very nice.
Yeah.
So, shall we move on to the main topic? The motivation behind it, because we have a few technical episodes that are more, it's fun, it's great, but I kind of want to make it little less technical and be more casual.
Yeah, this is just a fancy way of saying that we're all really busy and we didn't have time to properly prepare. We did.
We aren't supposed to reveal.
Sorry?
We aren't supposed to reveal our secrets.
No, we did prepare for this. a little bit. Not as much as we usually do, but it's still a good amount.
Well, the main topic today is about mathematics because the previous episode, in a way, have used a lot of math that we didn't talk about, which is interesting because it's really hard to talk about math in a podcast format. Even in any format, really, is difficult if the audience doesn't like really know what you're talking about or have a lot of prior knowledge, right? Like last time we had a lot of like quantum gravity, QFT. It's a difficult topic to chat about. So today we are going to be exploring the fundamental of what we do, which is mathematics. And I know that we all have different experience in mathematics, hopefully. But one thing as physicists or scientists, usually, a typical scientist would be somewhat well versed in mathematics. Maybe mathematicians would say, "Well, we don't know how to do math," but we do to a good degree that we can do our
It
job.
depends who you talk to and what you mean by math, because, like, I guess what a pure mathematician calls math, I might not call math, even though they're more correct than I would be. But when I think of math, I just think of like calculus and algebra because that's what I use most of the time. And I guess, group theory and things like that. But an actual mathematician might talk about how you have to like define axioms and use logic. And then from that, come up with theorems and ideas.
Well, the point I want to make is like, I think during our formative years when we were actually like young, right? We're exposed to math before science. Because to me, science has a very specific process. It's scientific thinking, it's scientific process. And we're not really exposed to that before mathematics. Everybody learned to count before they learn to do science. Come on, right? Everybody learned to add, learn to multiply before they even know how to form hypotheses, gathering evidence, right? You learn very fundamental math. Well, I see the smiles there, but the thing is, what was it like, right? Like in a way, we are mathematicians in the loose definition before scientists. So I want to open up the floor for more like, well, what was math like when we were young?
You might be able to argue that you were a scientist before you were a mathematician, because when you were a young child, even if you don't know what you're doing, you're kind of exploring the world around you and you're making guesses and you're kind of like, you can teach a kid, like, if you do this thing over and over again, you'll get a reward or something. If you really, I mean, maybe that's a bad way of parenting, I think, but I'm not going to get into that. You shouldn't feed your kid candy to make them do what you want. But a kid, like, they learn and they make hypotheses without actually knowing they are, I think. I don't know. I don't have a kid.
Well, I think, okay, our skills in mathematics was better than our skills in science when we were like 8 years old, for example, right?
Yeah, I know what you mean.
Yeah, so let's say we are more comfortable with math than science, because when we were young, we learned that science has so many different like fields that are like complicated. But mathematics at the time, because we were kids, right? There was like, these are the tools, well, the math you used, and I didn't see like the level of advanced math in a way, right? Like not even now to me, advanced math is just like, it's still symbolic. A lot of things looks the same, but science though, physics and chemistry looks different. Physics and biology looks different, right? Look very different. You could argue for the same for math, but when we were like 8 years old, it didn't feel that much different, at least to me.
I feel like one difference between getting taught math and science in, say, like elementary school, for example, and this is really testing the limits of my memory. I barely remember elementary school, or even like early middle school. So like grades 1 to 7, say. I remember never using math in science class, which I guess makes sense. You're still learning how to add and subtract and multiply. So when you do science class, it's more so you're just kind of talking about, you're like, oh, here's a tree and it takes sunlight and gets energy from that. You don't really ever put anything into like kind of this rigorous scientific language, and not even just math, but like even symbolic language. Usually, you mostly just kind of talk about things and look at pictures, like at least from what I remember.
Well, my grade school science is more like history, right? It's history of the world.
Really?
No, because like you said, there's no math, right? So what is it? It's like history. The teacher came in, tells you about trees, right? They tell you about the sun. They tell you about photosynthesis. They tell you about, maybe a little bit of the physics stuff. I don't know, particles. But in a way, it's like a history class, right? You sit in and here's like, oh, this is what other people have figured out before. But mathematics teach you more like a logical methods to perform operations, for example. And to me, I really loved it when I was a kid, right? Because you get to do something. It's more than just memorization. You get to engage in these numbers and things. You get books that basically glorify the number one. It's like number one is a great thing, and number zero is a great thing, and you learn about the history of math and how to me how to multiply was actually amazing. It's like, wow, you can add multiple times.
Yeah, I don't know about Patrick, but my experience with math was more so just learning algorithms instead of thinking critically. Um, at least when I grew up, it was very much like I had all these old school teachers, and it was all about just like pounding out a ton of exercises and getting the algorithms down, which is that's a good strategy for some people, not so much for others. But it didn't really invoke critical thinking. Like you're saying that you read books about what the number one and zero is. It's like I didn't think about that until I was in university, kind of thing.
Well, I think your point about critical thinking, I think it depends on the person. 'Cause I've done
Yeah.
a lot of like exercises and those stuff, but what I got for it wasn't just algorithm, right? I get to really think about it by doing the repetition. So let's say you're doing multiplication exercises, right? And you do like the same method or similar methods to different numbers. So what happened was that I started to recognize patterns, right? And that to me invoke critical thinking. Made me think like, oh, this is how multiplication works. It's not just learning algorithm. Learning algorithm is easy. It's like the first 10 minutes, people will probably get it, right? You just do the exact same method over and over. But the point of doing multiple times is so that you have basically more sample size to see how the algorithm actually come about and how it works. Sometimes it's really difficult to explain. Like teachers, if they spend time to explain the logic behind algorithm, then it could take forever, or it's just not very effective. To me, I think it's good to just leave the kids figure out on their own. It's like, here's how people do it, right? Here's how to build a table, right? What does it mean to build a table? If you build 100 tables, you start to understand what is a table and how it comes about, rather than it's like telling people this is a table, memorize it.
I think one thing that stuck for me was like little experiments that you do when you're younger, like the ones that you get you interested. Like the local chemists would come to your school and drop a banana in liquid nitrogen, and then it would shatter on the floor. I say the local chemists, like some chemists from somewhere, from some university, some like first year chemistry students or something. That stuff really got me interested in science. And one time, maybe I was a bit older when I did this, but it was still when I was a kid. I went to some community college somewhere, and we went to like an engineering lab, and they had a competition, and they gave us a bunch of Lego and said like who can build the strongest bridge, and then you put stuff on it and see who's lasted the most before falling into like a bucket of water or something. And I remember like trying all these different designs and kind of coming to a conclusion that like, oh, if you put like trusses in certain spots, it helps support the weight better and things like that. And I thought that was like really good critical thinking exercise.
But in terms of math, though, math is more abstract, right? That's why I think
Yeah.
it's less approachable to people when they were young, because not everybody would find joy in just like, oh, I figure out this algorithm works this way and I can do a bunch of things with it. That doesn't sound appealing to, I think, a lot of people. That's why I think there are fewer mathematicians than other disciplines.
And also, one thing which I'm sure that you plan to touch on, but I'll just say it now anyway, is that even as like a really young child, I remember everyone always talking about how awful math was. So when you go into it, you're kind of like you're setting up the kids to not like it in the first place. Like I remember like I come home with some math homework and like my mom would be like, "Oh, I hated math. It was awful." And like they would just like it's not obviously she didn't try and make math awful for me, but like it's just not something some people think about. Is that it has this very negative stigma, I guess, and as a kid, you're very easily influenced.
Yeah, I think that didn't really happen to me because I think my friend group we all quite like math. Even I have a really good friend at the time who was like terrible at math, who didn't really like it at all, but I liked helping him. And I think my family also played a part because I think my dad's an engineer, my mom works for a bank, so they're pretty good at numbers in general. And I think they understand the importance of understanding mathematics. And so to me, like math homeworks, exercise never seemed like a chore. Like the author science seemed like a chore at the time. It was like you have to write all these, memorize all the things. Math. I remember one algorithm, right? And I try to understand one algorithm. I can do an entire assignment or like next 10 assignments if you know how to, let's say, do long division, because the whole semester is about dividing stuff. You just like build on the knowledge of long division that you had in the first week.
I think growing up, I was the exact opposite of you, Feely. I I remember like having competitions, like we had math minutes in school where we had to do, I don't know, like 30 multiplications or 30 additions in grade 1 or 2 or 3, where you had to do everything in a minute. And then you were marked if you were correct or not. And I remember those were fun because they were competition. But growing up, and even sometimes to this day, I'm not really the biggest fan of doing math. It's cool what can come out of it, but I was always more interested in science and how things work and trying to figure out how things work. And so I remember from like starting to learn about science, like ecosystems or even engineering things, like, oh, this is how these different machines work, approaching it from a systematic perspective where it's, okay, these are the different systems involved and the subsystems, and these are how they all work. And there definitely was math in there, but I kind of didn't pay much attention to that and tried more so to understand how they work. And that fascinated me. I also like memorizing things a lot, where like I would just spend an afternoon just reading through capitals of countries and then seeing if I could memorize them. But oh no, I it could be very well be the education that we received. We were in very different parts of the world, and for Liam and myself, the country, we didn't really have chemists blowing up bananas in my school. But yeah, no, it's just interesting to hear that perspective, because I have the exact opposite one where, oh yeah, science was super cool, and we would always like try and do experiments, and I would go over to a friend's house and we would do experiments like, ooh, what can we dissolve in a thing of vinegar, kind of thing. But we didn't really go home and say, ooh, yeah, let's do our math homework right away.
Yeah. So like I'm a bit of a sine wave. I started off like that, like the same kind of thing you described, Patrick, where I could do the math, but like I didn't really think about it much or care because it was just some algorithm, and sometimes I get it wrong and sometimes I get it right. I just didn't think too hard about it. I was more interested in just like looking at things and doing little experiments. I'd go in the backyard and I'd like poke an anthill with a stick and see what happens. And but then as I got more into like closer to high school, I kind of went the opposite direction. I started saying like, oh, math is super cool. Like I really like theoretical things. I like how you can model the world. I thought that was super cool. And I kind of started getting away from the real world a bit. And then during my undergrad, I went back. During my undergrad, I kind of halfway through, I was like, oh, theory and math is really cool, but it's really cool that I can model the real world. And I start focusing on like the connection and trying to have more physical intuition than mathematical intuition. So I'm at a point now where I like math, but yeah, it's just a tool for me, kind of thing. Like it tells you a story. It's like a book. You see an equation, you're like, all right, my job is to kind of pull out the details of this equation to tell me about the real world. Went on a bit of a tangent there, but
Well, I think it depends on. I think it's really highly dependent on nurturing or like the experience growing up. Because to me, maybe mathematics, the reason why it attracts more introverts, because, you know, I think I was more taught, or that my impression of the world when I was young was this dark and dangerous place, and the safe place is home, right? And outside things are out there to kill you. There are animals and things. I wouldn't want to go into the backyard, has a bunch of bugs bit me, I die. It wasn't. Well, I mean, I was a kid, right? So I was like, oh my god, all these crazy stuff. I'm not Liam who wanted to go outdoors that much. I do now, but back then it was outdoors scary. Dogs are scary because rabies and all these stuff you learn about, and then the refuge is basically inside our mind. I think that relates to a lot of people in a more like theorists, right? Like you go back to your mind, and if something is fascinating, like puzzles, for example. Mathematics algorithm are a way to solve puzzles. So you solve a bunch of puzzles with numbers in your head. And to me, it was really fun. Maybe that's why I'm like still a theorist, because I still see all these outside things, just material, physical stuff that just not as valuable to me as my inner thought. It's weird, but I think I'm not alone. The people that share the sentiment that the abstract kind of hold more value than the physical. But hey,
Yeah, it's funny that you mentioned like the dog thing, right? I guess depending on where you are makes a huge difference, because like you grew up in Bangkok, which, right, like some massive city. So like I think if I grew up in a massive city as a small child, I probably wouldn't be roaming the streets at night, kind of thing. Whereas I grew up in a small town, so it was very much there's lots of nature everywhere. I would be out all night sometimes, maybe against my mother's wishes without her knowing, but you didn't hear it from me. Um, like just we'd be doing stuff like my friends and I, we'd be just like walking through the woods or like at the beach or just random things like all the time. So it's I think yeah, it's like everything in the world, right? Every person is so extremely different that everyone has different experiences. But maybe we should ground ourselves with this conversation and come back to some key point instead of I feel like I'm just rambling.
Well, going back to a key point that Feely brought up was the fact of nature versus nurture. Like, of course, there are some people who brains are wired a bit differently and will naturally get some algorithms within mathematics or concepts within mathematics easier. But nurturing and having a supportive environment for mathematics has been shown to improve scores in mathematics. There's been studies, and also anecdotally, there's lots of evidence towards this. But just from my experience, I had non-math people as math teachers, which I think is a big problem, especially in Canada, where we have people who had their educations in social sciences or in non-science
Yes.
related topics that are teaching math. And so, much like your mom, Liam, there are people that do not like math that are teaching it. And so that comes across to the students as, oh, well, this person doesn't really know how to teach it effectively, so I don't really need to put an importance on it. Whereas there have been studies that have shown that kids who are surrounded by like math at a young age can do calculus. They may not fully understand what's happening, but some parts of calculus are kind of more visual and easier to do than others. And so you can have these like 10-year-olds who are able to do calculus quite well and understand the algorithms behind it because of the fact that they were able to have this nurturing environment towards mathematics.
Yeah, I want to clarify. Like, I say my mom said she didn't like math, but my parents are still both better at mental math than I am. I'm very bad at mental math. I'm a very like visual person. I have to write it down to do it. But my parents did a very good job of the nurturing thing. So they made sure I always had like science books, and they were always talking about stuff they'd see, and they had these like little whiteboards where you'd have like math questions to practice on them, and um there's some other point I was gonna make, but the point is that they did a pretty good job, and I think it paid off actually. And one thing, actually, I remember what I was gonna say is that musicians, when you do music, you're kind of inadvertently doing math, and there's actually I don't have the papers in front of me, but there is a strong correlation between people who are good at math and music, I think.
Well, I was gonna bring up music too. Well, I was gonna bring up the
Okay.
natural aptitude for people, right? And the thing is, to me, mathematics is part of one of the very important part of the crucial fundamental education, because there are, at least for me, like required music classes when I was younger. Everybody has to pick an instrument, even though they're bad at it. I think I first picked up piano, and I had really bad teacher. I was terrible at it, and it was really discouraging. So I understand when you don't have an aptitude for something. I think I could be okay piano player, but well, at the time I didn't have a good teacher. In retrospect, so in a way you can see how people develop kind of disdain to classes, right? Like it's about communication. I hated going to piano classes because I get yelled at. Like what's the point? It's not fun. The music, the pieces are so like rigid too. You gotta pay everybody play the same piece, press the same keys, but why am I getting yelled at? So I feel like a lot of people feel that in their science and mathematics career, or like education when we're young, they're just bad at it, and people keep telling them they're bad at it. And I actually don't know how to fix it too. I think one of the main things that Patrick mentioned is that getting people who actually knows how to do math, because math to me is a bag of tricks. The bag of tricks. You're teaching little tricks to kids, right? Like here's how you build Legos. Here's how you build a pyramid. Here's how you build a square. But abstractly, here's how you multiply. Here are five different ways to multiply, but one may work for you, one may not.
I think it's like that with everything, not just math. But yeah, like that's a big one with math. Even I've said this before, but even to this day, like if I go, when they ask what I do, and I say, "Oh, I'm a theoretical physicist," the first thing they say, without a fail, or like 99% of the time, they're like, "Oh, I was really bad at math and physics in high school," and I'm like, "So you're just before you even like say anything about yourself, you're just telling me one of your weaknesses immediately." It's like you go into, you're like Achilles and you go into battle and you're like, the first thing you're like, "Oh, by the way, don't hit my ankle. It's my weak point." It's like, come on, man. Like, yeah, but for me it was language. So I don't know if they were bad, but they felt bad to me at the time. I had very bad like English and French teachers growing up, and maybe they weren't bad and I was just a bad student, but the French teachers were kind of these people who had took French, like one or two French classes in university or something, or college, and then they were teaching it, and they definitely shouldn't have been. You'd like go in the class and they'd be like, "Bonjour." It's like, oh my god. Like,
Yeah,
yeah.
no, I think teachers and the way in which we're educated is extremely important. And it might be very interesting to do an episode on pedagogy, which is learning about how people learn. And that's very important for teaching. I've been fortunate to take some teaching courses during my time at the University of Alberta, but it's fascinating to see some paradigm shifts that are happening in terms of teaching. And I know, having gone to a small university, the three of us, we got to experience something very different than what they're experiencing at this large university, where the teaching is more of a conversation, where you have six people in the class. And um, I fondly remember, especially Dr. Vandenhugen's classes, where he's like, "Okay, we're going to work this all out on multiple different blackboards." But it was a very conversational class from what I remember. And I believe that was partial differential equations. But even the type of style is changing of how people teach. And unfortunately, there's a lot of funding issues and finding enough teachers. But it's just interesting to see the shift in how things like mathematics are approached in terms of teaching, and the different styles that are approached, where it may have once been, "Okay, we're just going to do this 100 times until you get it." Whereas now there are different methods for teaching for different types of students and different types of learners.
Yeah, the thing about teaching in the past and now, I think what's different is that we realize, teaching is like getting students from A to B, like, point A to point B. And having curriculum or a lot of like rigid teaching plan is like paving the path for them, right? Follow this path. But then you realize people are like random walks. They just run around, right? Try to get to A to B. Some people really good following that path, which fortunately for me, I love how it's being taught, how like that rigid format that worked for me. But I understand this worked for a lot of people. And some of those ended up being excellent mathematicians, but they just look at things different way. So like the fact that things are more conversational and encourage people to engage, I think is very good. But it also has scaling issues. For example, like we said before, like Patrick said before, it works in smaller places, you have fewer people. Imagine you have a class of 1,000 people. Well, you can't have conversational class. It's gonna take forever. Nothing is ever gonna happen.
Yeah, I think one way, I don't want to say around those problems, but I think the more kind of well-rounded you are as you grow up, the better you kind of can get at science and math. I mean, obviously it's not true for everyone, but if you just hyper focus on one thing, you have no outside perspective. And like the point I was trying to make with music is that if you learn an instrument and you also kind of do science and math, that's like a new way of viewing things. And I don't know about you guys, but that helped me a lot. Like at least with certain things. And if you speak another language, which I do not, maybe one day I hope, but it's you can adapt a lot easier. You know how to think about things in different ways. You have different viewpoints, and I think that's crucial in science, and even math as well.
Yeah, I think there are a lot of adjustments that can be made, and part of it is being adaptable and learning to be adaptable in terms of your learning style, but also recognizing your learning style. Just quickly, anecdotally, my first semester of calculus was awful. I believe Feely and I were in the same course in the first semester for calculus. I wouldn't say the professor's name.
I had no idea.
Yeah.
I had no idea you were in the class.
Okay. You were the guy that fell asleep in the front of physics, so.
Yeah, we know who you were because you were always passed out in class at the front.
But yeah, I remember that the professor would just write on the chalkboard for the entire class, barely face us, do very little examples, and just go through the proofs. And my mark reflected that, whereas I learned by example. And so in the second semester, I had an excellent professor who would like make us do practice questions in class. And he would like ask us to do the answers up on the board. And it was very interactive and just a very different teaching style. And that was more beneficial. And so my mark reflected that as well.
I got the opposite experience. I thought that calculus was amazing, fantastic. As a person who just came in knowing little like conversational English, he was like really gradual. He writes everything down on the board exact verbatim, so I can just take them down and just like try to understand it. I don't need to do I can do examples on my own, right? You can just anyone can open a book. At least for me, that was my experience. I just need to learn the actual, the text, and I everything I can do it by myself. My marks reflect that. I was amazing, and compared to a more conversational class, which I struggle with. I think I took like a bio something, and I was just like, there's like so much talking, like who's right, who's wrong, right? As a young person, I had no idea. I just need someone to tell me. It's like, hey, all right, here's the knowledge, take it. And it's just a different style. And you can see even for like the sample size of 3, like us, right? We have so much contrast.
Yeah, and that's the problem. Is that like in a perfect world, the prof or the teacher, they do all kinds of different teaching styles and they help everyone out and there's extra resources, but reality is that each teacher or prof has a very different style based on what they like, and maybe amongst the 3 of us we have extremely different tastes. So imagine you have like a class of 200 people, right? You're not going to hit everyone, and that's kind of just the way it is. And the world's getting better at solving those problems, but everyone learns differently and in different ways, and I think if you can be adaptable, then you've got a much better shot than everyone else.
Yeah, I think that's what the difference why Patrick doing more practical stuff, because like let's say people want to teach me how to use a hammer, right? For you guys, Patrick will like, oh, show me how to hammer things. But I was like, no, show me on paper. What is a hammer? How's a hammer work? And I would figure out how to use a hammer. That's how I prefer. To me, it's like me with math. You don't need to show me examples how to solve the problem. Show me the theory behind the tools you want me to use to solve the problem, and I will use it. You don't spoil it.
I think I'm somewhere in between the two of you, honestly. Like, when I started my scientific career, I was very much like, I have to do it to learn it. If you just tell it to me or I put it in like equation in front of me, I struggled with that a little bit. But as I've gone on, I've gotten better at actually doing both things. I've tried to make myself very adaptable. I tried to be able to, like, you put something in front of me, and at the very least, I have some idea of what's going on, no matter how you present it to me. But again, it's different for everyone, right? Like, I've had very good profs, I've had very bad profs, but those bad profs were good profs to other people, and it's interesting.
Yeah. I mean, I think my way kind of helped me in grad school too, because like a lot of exercise and problem are not as straightforward as like fundamental education anymore, right? They just give you like, oh yeah, now you know the basic of quantum mechanics, a bunch of problems which doesn't look like you can solve at first. And I think it was to me it was quite fun to tackle those problems because it's like the path has never been shown to me before how to solve it. But I understand that like it can be very frustrating for people. It's like, oh, it's not taught in class, but technically, the tool was there. It just needs to apply it, which can be extremely difficult.
Just as a little comparison, it's like your whole life you've been using a hammer to just hammer nails, and then you're asked to pull out a nail, and you're like, how do I do this? You're given the tool, it can do it. You just need to figure it out.
The next thing I kind of want to touch on is that, we all have pretty decent mathematics background. And at some point in our lives, we probably was encouraged to join the engineers, right? To took the path of engineering career because, at the time, well, I think still now, it has a pre-prospect of having a bright future in terms of even financially, in terms of like, career path, what you do to the building things in the world. So why didn't we join engineering?
I don't know why, but my entire life I've always been one of those people who I like doing kind of niche things. I mean, like I'm a bagpiping physicist. I don't know. They're two random topics. Well, you are too, Patrick, right? Like maybe we're the same. It's funny because I've only met two other people in my life who are physicists and who play the bagpipes. And one of them was this 65-year-old retired physicist from Australia. And then you. And you and I happen to be in the exact same program at the same university. So I don't know what God decided that, but pretty funny.
I mean, I do pretty niche stuff too, right? Like, I play a little bit of classical guitar, which for those people who play guitar, they usually pick acoustic or electric guitar. But to me, it's like, well, it's kind of same notion, right? Like, I just didn't want to engineering just because engineering to me, building stuff is cool. It used to be really fun when I was young, and then I just lost interest in it. I was like, well, I know it's possible to be made. I just get people to make it, or the design part of engineering just doesn't. Well, okay. To me, figuring out fundamental of the theory behind it is just much more enjoyable than try to make it practical.
Yeah, I didn't think that deeply about it. I just saw that in my physics class, 9 out of 10 people wanted to be an engineer, and the other 0.9 people wanted to do something that wasn't physics or engineering. So I really liked math in high school. I got into it a bit more than I was in middle school, and then I really liked physics because it was just using math to solve problems, and I thought that was really cool. And I thought engineering would be fun, but I thought it would be kind of boring after a while because in my mind, if I know that's not the case. Yeah. So I kind of just like I wanted to do. I thought engineering would be fun. I thought it would be challenging. I thought it was very similar to physics. And in high school, you tend to not know exactly what you're getting into in university, which is actually a whole other problem for some places that we could talk about for a long time. Like my high school did a very bad job of warning you what university was like, and specifically if you're doing some kind of degree, like what that degree is like. But in my mind, I knew that, or I didn't know, but I figured I'd get bored of engineering pretty quickly, and I think I was wrong about that. I know engineering, depending what field you go into, can be very challenging, and you get like new things happening all the time. But in my mind, an engineer was like, oh, I wake up, I go to a building site, and I check structural support. And that was like, in my mind, that's what an engineer did, even though that's quite wrong for most engineers. So I was like, physics, that'll be fun, you know? It's like cutting edge stuff like black holes, like particle physics, relativity, quantum physics. I thought that was so cool.
To me, part of me, maybe introvert part of me, is like, I don't like to be recognized. I hate people know me. I hate fame. I don't want to be really known in a way, because like I used to do like operating light and sound system for the school, and you or do photography for the school. So you're in the background, right? Things happen because you're there, but not for you. So you help facilitate that. And to me, at being a physicist or scientist, you're in the background in a way, because you see these engineer, architects, or workers who build the world, like design and build the world as we see it right now, the physical buildings and stuff, and they get a lot of recognition, which is great. But I want to be the physicist or scientist in the background, digging up all this knowledge from nature and get people to use it without really, not in the front line or anything. That's the plan. That's why I like being scientist and physicist.
Until you win a Nobel Prize, and then you get very, very recognized.
Well, the problem, most physics Nobel Prize winners always complain about how little time they have to do their research, because everyone just wants to hear about what they won their Nobel Prize for. And the physicists are usually just like, I just want to go back to my lab and do my math and experiments. Leave me alone. I mean, some of them love it.
Let me go back to my basement, my deep, dark, humid basement, and churn out more theory and paper. Like, this is what we want to do,
right? For me, I was kind of chasing the fame, not really, but the idea of a Nobel Prize was very luring into physics. But I was always interested in sciences. I remember being interested in environmental sciences at a very young age, and it's funny that kind of came full circle. But I remember thinking that, oh yeah, engineering would be cool, and they get to build stuff. And then the Large Hadron Collider, I remember reading like an article in an astronomy magazine about it, and it's like, oh, I don't have to be an engineer to build some cool stuff. And I also get to like test the stuff and make the stuff and essentially be in control of the whole process from the building of whatever it is all the way to the end. And well, naive young me thought, oh yeah, I could like totally help build the Large Hadron Collider or whatever comes next single-handedly. Because I do love that aspect of building, but I also love the aspect of experimentation. Also very similar to Liam, where like 90% of my physics class wanted to go into engineering. The other 0.9% didn't want to go into physics. I think I was one of the only students who actually wanted to go into physics and was passionate about it. But yeah, it's funny that we also all have the same undergraduate education, but we got very different things out of it.
I was used to dream. My hopes was like, be like the recluse, like a reclusive hermit on a mountain somewhere, and it was like the people try to figure out how to go to another planet. It was like, we couldn't figure out. Let's go to this guy. Walk up 20,000 steps out his door. Knock, knock. We need to go to another planet to survive. It's like, here's a paper. Here's how you warp drive. That's so cool. And if you don't know about it until you go to this, but I think it's a good time to start wrapping up because we have a story. So, any final comments?
Conclusion: people don't like math for dumb reasons. It's not their fault. It's the world. Don't hate the player, hate the game.
And if you have kids, teach them math early. And don't say you hate it.
Let them play an instrument. Sure, they'll suck at it for a while, but once they stop sucking at it, it'll be worth it. And if they decide they don't like it, then they'll just stop playing. So what is there to lose?
Well, even though I didn't learn that much from some music classes, but I learned discipline, right? It's education is not about learning the theory or practical instruments or how to operate things is also learning how to live, and discipline is part of the very important part of life. Anyways, so before we get to the story, I'll get Patrick to tell you guys how to reach us and how to contact us.
Right. Well, if you have comments or questions or concerns, or if you're an expert in pedagogy or education and you want to be on the show, feel free to send us an email. We're hyperthesispodcast@gmail.com. We check that pretty regularly, and we are always open to having people on the show that are wanting to talk about their areas of interest, whether it's teaching, mathematics, physics, or whatever kind of science-related topic it may be. We can also be reached at Instagram. We are at the Hyperthesis. We post updates of when our shows go out, as well as some behind-the-scenes looks. And Liam's been more on top of the memes lately, which are spicy, as the kids say. As for contacting,
Poggers.
oh boy. As for
PogChamp.
for contacting us otherwise, we are also on YouTube. We are almost caught up to our live release date, so thank you, Feely, for processing those on your lovely MacBook. Pretty soon we'll be processing those videos in the, what's it called, Studio Goggles or Apple Studio Pro, whatever their new VR headset yet, which has an M1 chip in it. We can be found on YouTube. Feel free to give us a subscribe, a like, a comment on the video. I believe our videos all have commenting. If you want to listen to us, we are based out of Spotify, but you can listen to us wherever you find your podcasts, whether that's Google Podcast, Apple Podcast, Audible. We are on Audible now. We just found that out last week. And pretty much any podcasting service that you may listen to. So subscribe, leave a review, leave a like, whatever you can do on your podcasting service, and check us out in our other social media.
Well, just a note, I think that headset is like $4,000 or something, so I'd rather pay my tuition than do that.
Anyway, moving on to the story. Oh yeah, it's like $3,500 US. Yeah. So we spoke about math today, and in the past we've spoken about a lot of math-heavy topics. And today I want to focus on another famous mathematician. We've talked about someone who's very closely associated with this mathematician, but it's time that this mathematician got the limelight because he is a major factor in the development of calculus, and some say that it might have been him, it might have been Newton, who really developed the core ideas behind calculus. It was both that we use today, but this famous older mathematician is Gottfried Leibniz. So Gottfried Wilhelm Leibniz was born on July 1st, 1646, so long before we had Canada Day. For those that don't know, Canada Day is on July 1st. So he was born in 1646 in Leipzig, which then was part of Saxony, not Germany at the time. And he was the son to Friedrich Leibniz and Katharina Schmuck. Now, Leibniz was then baptized, of course, as was tradition back then. But he had very good parents who surrounded him with a lot of education, much of what we were talking about today. And for example, Leibniz's father was the professor of moral philosophy at the University of Leipzig, and the boy actually inherited his father's library and was given free access to it from the age of 7. So he was able to explore these ideas in the library, and it was very uncommon to have access to so many books at the time. So he was able to start developing from a very young age ideas of philosophy and theology. And he was also very proficient in multiple languages, including Latin. At the age of 13, he was very well versed in Latin and was able to speak and write clearly in Latin, which is a dead language today. Now, at the age of 14 in 1661, he enrolled at his father's university, so the University of Leipzig, for his bachelor's degree in philosophy. So again, he was 14 years old, and he was already starting a bachelor's degree. And he defended his dissertation, the metaphysical disputation of the principle of individuation. That's a bit of a mouthful, but again, it's philosophy. And he actually defended this in 1663. So just in 2 years, he completed his bachelor's degree at the age of 16. Then he got his master's degree in philosophy in 1664, and he was able to publish the dissertation for that, which was an essay of collected philosophical problems of right. So again, very philosophy-based, and then there, in that he argued for a theoretical and a pedagogical relationship between philosophy and law. At the ripe old age of 19, he received his law degree, his bachelor's degree in law, in 1665, with his, he was 18 at the time, which was titled On Conditions. So at the age of 19, this is when he wrote his first book, which was on the combinatorial arts, which was a philosophy manuscript, but also contained proofs for the existence of God in a geometrical form. So these were the beginnings of his math career. So then he received his doctorate in law shortly thereafter, as someone who at the time should have, in our day and age, would most likely be receiving their bachelor's degree. He was a doctorate in law with a couple degrees under his belt. And he continued to stay in the academic world. He had different positions, including in the Alchemical Society in Nuremberg, where he was learning more about the subject at the time, and he was able to really dive into it. And one of his mentors at the time was von Boinberg, which von Boinberg was able to help Leibniz's reputation and essentially promote him up the class of who was well known, really helping Leibniz become better known, especially in the world of academics and free thinkers. Paris eventually went to Leibniz in 1672, where he met Dutch physicist and mathematicians Christian Huygens. Apologies if I mispronounce that. I believe we've discussed Huygens before. And at that point, Leibniz realized his knowledge of mathematics was patchy and wasn't really all that good. So Christian Huygens took Leibniz under his wing and began to teach him mathematics. And from there, Leibniz was able to start discovering things, including his version of differential and integral calculus. So there, he was also able to meet many other mathematicians and share their ideas. And things became a bit iffy for him later on, where he didn't quite necessarily stay in France because he didn't feel welcome. However, he was able to try to get admitted into the French Academy of Sciences as an honorary member, but it was said that there were enough foreigners in there, so there came no invitation for him, and he left Paris in October of 1676. He then went to Hanover, where he was actually invited by the royalty there, and he was promoted to the Privy Councillor of Justice, being a doctorate of law, of course, which is a post he held for the rest of his life. And this was, again, at the time, a very plentiful royalty in what we now call Germany. But Leibniz began to promote other scientific concepts like the use of windmills to improve mining operations, and he was also able to introduce many other ideas to the different royal families to help improve their lives based on his background in now math and philosophy and law. Now, Leibniz was also able to travel around a lot to different parts of Europe and share his ideas, but nowadays we most know him for his invention of his version of calculus, which we still use today, and is still commonly used by many, many students worldwide. Now, Leibniz died in Hanover in 1716, so at the time, he wasn't necessarily in the best graces of the royalty at the time, and no one other than his personal secretary actually attended his funeral. He never married, never had kids, and all of his wealth went to his sister's stepson. And even though Leibniz was a member of the Royal Society and the Berlin Academy of Sciences, neither organization saw it fit to honor his death, and his grave went unmarked for 50 years. So this is someone who contributed greatly to philosophy and law and a geometrical God figure. But unfortunately, he was not very well remembered for a time. There's been a resurgence of Leibniz support, especially with the thought that Newton didn't really invent all of calculus, in fact, borrowed ideas that were originally thought up by Leibniz. So there's still controversy over Leibniz, but he was certainly a very well-accomplished man and a well-accomplished boy. Again, having his different degrees by the age of 22 is just mind-boggling. But it's because of him we have modern calculus, and it's because of him that we are able to do science using math.
All right, thank you, Patrick, for the very important historical figure story. And I think that's the end of episode today. Take care.
Bye, everyone.
See ya.